Hello! Since it's the end of my exams, I thought we'd make a celebratory planet cake in the shape of the planet Saturn. To make this cake, what you need is a really large amount of cake making ingredients, 3 planet shaped sized balls, and a helpful helper in the form of boyfriend. Let's go! This chocolatey mixture is the core of Saturn. It's the rocky core, which is about 10 times the mass of the Earth, and mixed in with other ices and rocks and volatiles and things. There might be increased differentiation of the core, like a rocky, like a metallic center, but it's quite hard to measure the core of Saturn, so no one really knows. Here's the first half of the core going into the other. And it's looking for planet now. There we go. This dubious looking mixture is meant to be, well, hopefully will be, the metallic hydrogen layer. Hydrogen obviously isn't actually a metal, but when it's put under a lot of high pressure, then all the electrons can like dissociate and form like a little Fermi gas, like a sea of electrons like there is in a metal. So it becomes, I think our lecturer said to think of it kind of like mercury at room temperature, but we don't actually have the colour of a metal, so we're going to dye it green like in that picture. Also, Saturn gives off more heat than it should, and this can't be because of like heat from its formation because it's too small. It can't be because of fusion in its interior, like they think Jupiter's extra heat might come from because it's too small again. So it might be from continued differentiation in like the upper atmosphere of the metallic hydrogen, like evaporating and then raining back down, and then evaporating and raining back down. This is the last layer of the cake, which is Saturn's upper atmosphere. It's comprised of hydrogen and normal hydrogen and helium. Gas giants are the only planets big enough to contain or retain hydrogen and helium in their atmospheres, because they're light elements and they need a really large escape velocity to be retained by the planets. Also, they normally only form in the further out planets because of the solar wind, otherwise it would strip them off the planet's atmosphere. Which is really why it was very surprising when they looked at exoplanet systems and found that there was a lot of like hot Jupiters, which are these gas giants that seem to have like these big distended hydrogen helium atmospheres, but they're really, really close to their star. But it's thought that they formed further out, like our gas giants, but then kind of migrated in and possibly like destabilizing the whole planetary system and like pushing any terrestrial planets into the star. Taking the first one out the oven. One half of a core. Rings out of chocolate. How's it going? The look of concentration.
It's
going pretty good.
I'm a bit concerned about it though.
If anyone's wondering what this little gap is in between these 2 rings, beautiful rings with the smiley face in the middle, it's called the Cassini division, and it is due to an orbital resonance with one of Saturn's moons. Yeah, rings, there we go. An orbital resonance is like, normally when you have things in the solar system, they're influenced obviously by the other bodies orbiting around them as well, not just like the Earth and the Sun, but you've got the Moon, you've got all the other planets orbiting as well. But it becomes really, really difficult to solve the equations for all the planets. So normally you just like say, oh, they're kind of random, they'll average out over a long period of time. Like sometimes they'll pull on the Earth, sometimes they'll like push on the Earth. So you can just treat it as like a 2-body problem. But sometimes if they're in like small integer numbers of like orbits, for example, in the Cassini division, this thing's orbiting within that gap, and the moon Mimas, I think it's called Mimas, have a 2-to-1 orbital resonance, which means that they have a regular like pull or push on the thing. And there are 2 effects that can happen from an orbital resonance, and one is that it has a destructive kind of impact, and it kicks everything out of that orbit, which is what happened in this case with the gaps. You can see this in like the asteroid belt as well, it's called the Kirkwood gaps, and on plenty of other things. And then the other thing that can happen from an orbital resonance is it becomes locked in like a stable orbit. And for example, if the moon was in orbital resonance with the Earth, then it would get stuck, or a very stable one, like some of the moons of Jupiter. And instead of the Earth giving it slowly energy and it climbing out slowly, getting further away, moving out of its potential well, the energy the Earth transfers to, or that Jupiter transfers to its moons, all gets put in tidal heating of them, which like squishes them and deforms the crust and heats them up. So, for example, like Io, the moon of Jupiter, that has this like huge tidal locking with like a 4 to 2 to 1 resonance with these other moons that I've temporarily forgotten the names of, but I actually did know for my exam. It's like the most volcanic object in the solar system, even though it's really far out, obviously, well, quite far out in Jupiter. You wouldn't think it'd be that hot and that much activity, but it's super boiling. And this is also why there is potentially life on one of Saturn's moons, which you'd think, again, like there's no chance of life on Saturn's moons because it's icy cold, like it's not in the habitable zone, there's no liquid water there. But one of its moons, Enceladus, that's the little life, is in a tidal locked with another moon, this little one down here, which is why it's saying get off, gap, it's all of it. And this tidal locking like squishes and deforms the icy moon Enceladus, which causes cryovolcanism, which is like ice volcanoes. And this ice can be seen squirting out into space. And so maybe there might be a subsurface ocean and life. Push the rings of Saturn into the freezer. As expected, they don't fit. First half coming out. Looks good. This is the sky.
Oh.
Dawn has arrived. I think it's 4 a.m. or sometime after that. So
We're
cake
still not done.
making will resume in the morning. It's worth it though for science. This is the finished cake half, and there's another one that doesn't look as good as this, so we're not showing it to you. You know the rings that we iced yesterday, or chocolated? That's another way. I put them in the freezer, and they are now rock solid, and they've actually worked really well. Like you can see they're peeling off, and I put iced them and put little honeycombs and like rock bits on to symbolise the rocks and icy particulates that make up Saturn's rings. It looks kind of like a sad hamburger. Ta-da! Saturn minus the rings. Now for the rings. Ooh! The inside of Saturn. A world exclusive view.
No more presents. Here we go.
Yeah, here we come. And we just ate our evidence. No! Except I think it's probably takes a long time to eat this much cake. Yeah, I do. Ah, pretty successful. The metallic hydrogen layer may be a little bit more differentiated than was expected, but I think it's going pretty well. Saturn. I think the rings are my favourite. They're really tasty as well. Mmm. That's why we chose Saturn, the most prominent ring system of any gas giant. They actually all have rings, but Saturn's is really icy, so it's really visible.